Hi, I'm Ken Dulaney, Director of Industry and Innovation at the FREEDM Center at North Carolina State University, located in Raleigh, North Carolina, in the United States. FREEDM is a smart grid research center specializing in renewable energy, power electronics, electric transportation, and applications of wide bandgap semiconductors. My role is to manage our industry partnerships and help move our research to commercialization. I am also the representative for Reops on the LF Energy Technical Advisory Council. Today, I'm going to present some background information and describe some of the many applications on the Reops platform. And at the end, I have a favor to ask. Reops is the resilient information architecture platform for the smart grid, originally developed by Vanderbilt University and North Carolina State University, with initial funding from the U.S. Department of Energy in 2015. The vision was to create an open-source software platform to run smart grid applications. The platform provides a programming model, application services, and a development toolkit. It is designed around resilience, security, and distributed applications. From a functional view, Reops sits on top of an OS kernel on whatever hardware platform is necessary. For most of our research, we use BeagleBone Blacks running Linux Ubuntu. But it can also run on Raspberry Pi, and we recently implemented an industrial version on CON Bus Revolution Pi. The Reops platform includes the framework for component management and the management system for the platform. This is the system plumbing and includes component messaging, scheduling, and resource management, as well as fault management, time synchronization, and security management services, all the background coding required for the platform operations. This allows power system engineers to focus on building applications like energy management, microgrid controls, transactive energy trading, load shedding, etc. Each hardware instance running the platform and these applications is called a node. Just to emphasize again, Reops is a platform, and you can build applications on this platform. These applications can be written in Python or C++. You can also export code from MATLAB or Simulink. And if you are familiar with the LF Energy functional architecture, Reops is categorized in the edge node control block in the lower left with several other projects. But enough about the background. Let's talk about some applications. What can Reops do? At a very basic level, Reops, like other grid management tools, does three things: measure, actuate, communicate. But it does all this very quickly, which makes it appropriate for edge node control. There are applications for transactive energy, where distributed energy resources or building owners, for example, can make rapid trades on the economic value of energy. Utilities can implement under-frequency load shedding as part of remedial action schemes. You can implement any number of protocols in addition to those listed here. But Reops really does well in microgrid controls, and I'll describe some of those applications more fully. As a quick reminder, microgrids are a portion of the electric grid that are usually connected to the main grid, but can isolate when needed and still supply the connected electrical loads for a period of time. Some microgrids are the size of single buildings, while others include entire towns. This is the standard Department of Energy image to explain a microgrid. However, it is also helpful to explain what a microgrid is not. It is not an uninterruptible power supply, a backup generator, or solar panels individually. But you could combine all those technologies, add a controller, and create a microgrid. Conceptually, microgrids have several layers of control that extend from the very fast controls at the inverter level to slower controls for energy management. Reops is not used for inverter controls, but can be used for all the other layers. Reops can certainly interface with inverter-based resources, but not for the internal inverter management. The point of this diagram is to convey the timescales appropriate for Reops applications. So let me describe an energy management application we're currently working on. Let's say you have a building connected to a battery and an electric vehicle charger. As the building operator, you want to minimize your costs, but also make sure you still have power for building loads and to charge electric vehicles when necessary. Managing your energy requires communication between the devices and forecasting future electric needs based on weather and historical consumption. For this application, we built an interface to TensorFlow where we applied machine learning and optimization techniques to forecast load. We also coded a connection to the building management system to drop loads if necessary. The coordinator node includes a cost minimization function that can include battery state of health and remaining useful life. The system is modular, meaning more nodes can be added for additional EV chargers or other resources like solar panels. One of the benefits of microgrids is the ability to island from the main grid when necessary. This can include when the main grid goes dark or electricity prices spike. Many microgrids are designed for a short power outage before they black start in island mode, but some are designed for seamless disconnect and reconnect. However, the microgrid must be exactly synchronized with the main grid before reconnecting. These microgrids normally depend on a single large generator to dominate the microgrid characteristics and usually rely on centralized control. With Reops, we can build applications that allow resynchronization by coordinating voltage magnitude, frequency, and phase among smaller distributed resources. This diagram represents a system of 4 distributed resources with one that is designed to receive measurements from the point of common coupling. A pinning algorithm can be used to align the source voltages in real time while maintaining microgrid stability. Again, Reops is designed for resilience, meaning control is distributed rather than centralized, and nodes can leave or join the network at any time, and the system reconfigures itself as needed. A potential problem in microgrids with multiple generators is voltage unbalance. A typical solution is for one generator to compensate voltage unbalance by injecting negative sequence current in phase with negative sequence voltage. The issue is that the local generator controller must have a direct sensor connection to the compensated bus to measure instantaneous three-phase voltage. But physical distance can cause delays and negate the compensation effects. What if we could design a system to allow multiple distributed generators to share the duties of compensating voltage unbalance? If the instantaneous measurements are transformed to the DQ reference frame, then the DQ values can be transferred to the generator controllers via low bandwidth communications. Inverse transformation occurs with the help of the high precision synchronization pulse in Reops. You can see in the simulated results that differences in phase angles allows for gradual alignment between the remote generator controller and the distant sensor. So far, I've described a series of applications that can be applied to microgrids. Our latest project is to put all of these applications together into an integrated microgrid controller platform. This ambitious project is designed to easily integrate legacy devices by coding Reops-compliant drivers for those devices. The IMCP will support IoT technologies, advanced market structures and bidding strategies, machine learning on edge devices, and real-time analytics. As I've explained, Reops can be viewed as an operating system where anyone can build applications for real-time control. Physically, how did we do all this development and testing? We use hardware-in-the-loop simulators, which allow real-time simulation of power electronics and power systems. We use a field-programmable gate array for the inverter controller, a typical relay, like you would see in any substation, and wire it all together with each Reops node running on the BeagleBone Blacks, receiving inverter signals through the Texas Instruments digital signal processor boards. In reality, it means wiring these boxes to these boards and hiring a tireless graduate student to work long hours. But we've also moved beyond hardware in the loop to a lab-scale, complete hardware demonstration. At Freedom, we have what's called the Green Energy Hub testbed, which is a full hardware implementation of our microgrid, complete with battery storage, programmable loads, solar panels, and a Reops-based controller. Our controllers here have the same hardware as those in the HIL environment, but rather than simulated inverters or simulated battery performance, we have actual hardware. Reops can be used in just about any situation that demands real-time control. Utility DERMS, clusters of microgrids, or even single home microgrids are examples. Some Reops features come from systems built for operating the International Space Station, which requires extreme reliability. Utility operators and industrial process controls have similar reliability standards and thus make good candidates for Reops deployment. Our roadmap includes the standard goals for any open source project: connect to other projects, attract more corporate and independent users to build community, and move to the next phase of the project lifecycle. So how do we make progress on our roadmap? We can only do it with your help. As you have learned, Reops is a powerful platform that works really well in the lab environment. And Vanderbilt and NC State are in the process of implementing several pilot demonstrations outside of the lab, but we need to grow our community. If you are interested to join the conversation, please subscribe to the Reops mailing list. We are planning training sessions this summer, but need to build an audience for those sessions. Email me if you are interested. We are also planning a university hackathon for the fall. We hope to hold this in person, if at all possible, in either Nashville or Raleigh, the home cities for Vanderbilt and NC State. Again, share this presentation with your friends at university and have them contact the Reops team or myself directly. Here are some resources where you can learn more about the platform. We obviously have a GitHub page. Our YouTube channel includes demonstrations of almost all the applications I discussed. The Reops email list is not very active currently, but we are working to increase that activity. This concludes my presentation, and I appreciate your attention. My email is kadulane@ncsu.edu. Now we'll shift to the question and answer portion of this session.
All right. Well, thanks everyone for watching the video presentation there. Either I did a fantastic job or I didn't actually present the information in a way that generated questions. Doesn't look like we have any so far. I am happy to answer those, and we'll hang out here for just a little bit. One of the issues that I've addressed somewhat in the video that I presented is that, you know, this is a very academic platform. I mentioned we can use the programming in Python or C++. The issue with, you know, a platform like this is that you have to be a power systems engineer who understands power systems and protection schemes and, you know, things like DQ reference frames. And you also need to be experienced in coding in Python, or at least have, you know, some understanding of how to build those algorithms in a programming environment. I don't think that's any different from some of the other open source platforms that you're learning about here as part of LF Energy. You know, power systems are difficult, and that's why it takes electrical engineers to help design them. But our project in particular is still in the academic environment, which is why at the end of my recorded presentation, I did ask for basically help. You know, it's currently the Reops supporters. It's myself and a couple of faculty. We've got several grad students, a postdoc that's working on this, and we are moving towards pilot scale demonstrations and, you know, implementation outside of academia. But we need other ways to get a user community interested in learning more about our platform. So if you're still watching this, maybe you could put some ideas in the Q&A or the chat. as far as ways that we could generate more interest and get more people involved in the Reops platform. So I'm going to be patient here for just a little bit. Any questions on implementation or how we use the coding or anything? Hopefully I'm actually live and everybody can hear me. Maybe that's the first thing I should ask. Here's a chat in the session. Thanks, Carly. I appreciate feedback that at least you guys can hear me. That's good. Yeah, and Celia agrees that my presentation was thorough. I find that hard to believe, but I appreciate the comment. All right, well, I will hang out for maybe one more minute just to see if anybody does come up with a question. You can either put that in the chat or in the Q&A. And yes, I agree, go NC State, Wolfpack, all right. And it would certainly be okay to contact me afterwards. You had my email there. It's and I'm also available through the FREEDM website. But the email, yeah, is kadulane@ncsu.edu. There's a question here about being on Twitter. The Freedom Center is on Twitter. I personally do not have a Twitter account. And I do not manage our center's Twitter account. Well, the good news is, all right, thank you, Carly, for that note. Like I said, everybody should have my contact information, so I will give you back a couple of minutes to your day. Maybe you can grab another cup of coffee or get a quick bite of lunch before we move on to the next session. All right. Thank you, everyone. I look forward to engaging in the future. Thanks. All right. Well, thanks, everyone, for joining, and for some of you for suffering through my recording twice in one day. That's crazy. So I'm Ken Dulaney, happy to answer any questions that anyone has. I do have one which someone put in the chat from earlier. How does Reops relate to other LF energy projects like Sueño, GXF, and Operator Fabric? I think the easiest way to do that is, well, the answer is we don't yet. So Reops is, like I said, on the edge node control. GXF is more for data exchange. Operator Fabric is, again, to my understanding, more of a way to gather data and present relevant information to grid operators. Reops would be on the edge of the grid. So could be used as a distributed energy resource management system, a DERMS, which could be gathering information from those edge devices and feeding that into something like GXF or Operator Fabric. We have not yet programmed the interties between those, but that is, again, part of our research roadmap. I was thinking that what I could do is also just show you guys real quickly. This is the that figure from earlier, which is just part of my presentation. But you know, the Operator Fabric is over here in the shared operations area. You know, GXF is down here for gathering information from all of these edge node devices. And I am actually not sure where Sueño is. I think it is maybe in the asset management system. But the point is we have the capability to make those ties. And we talked about, linking directly with Fledge. But again, we're not quite there yet, and don't really have the user community that we need to be able to build a lot of those interfaces. So here's a question from Frank. Does Reops make any use of the PRUs in the BeagleBone Black, or are most of the real-time tasks offloaded to the FPGA? So the FPGA was just for the simulation, the simulated environment, the hardware in the loop, and that allowed us to provide the inverter capabilities, or to simulate an inverter rather than having a real inverter as part of that system. And unfortunately, I do not know what a PRU is. So maybe Frank, if you wanted to put what that is in the chat, maybe I could answer that a little better. So one quick point of clarification. For my background, I work with all of the people that do the programming in Reops, like the tireless graduate student there, and the two faculty key principal investigators from Vanderbilt and NC State. But I am not a programmer. I've seen it done, but I'm not into to using Python. Programmable real-time unit, basically a microcontroller. So that's what PRU stands for. I would say that in a real-world application, yes, we would use that as opposed to something like the FPGA. I hope that answers your question. Any other questions? I did put in the chat that I saw a lot of the individuals from the microgrid special interest group, which has been meeting to talk about microgrids in general. I know I haven't been attending those meetings lately, but I've seen that you guys have had some good discussions about microgrids in general. So I will be patient and hang out until we get some other questions. James asks, when will Reops run on Kubernetes? That's a great question, James. Don't know. Right now, we're still working on the individual Linux boards, like we've got it working on Raspberry Pi, we've got it working on the BeagleBone Blacks, but have not translated it to Kubernetes. And again, I know we've had other requests to containerize Reops, and that is something that we could do and have talked about doing, but again, have not done that yet. So let me know if that answers your question. Okay. Do we want help containerizing Reops? Thank you, Frank. We would certainly love to have that discussion. And it's, some of those initial conversations came up when we were talking to Monash University about the microgrid that they are deploying on their campus in Melbourne, Australia. And that was a couple of years ago when we started that conversation. But yes, I would say we would love to have the help. If you want to send me an email after this, I can put you in touch with the right people to have that conversation. And I know that there are advantages to being able to do that, but we've just not made that jump yet. Some of the parts and pieces that I did not mention in the presentation for that integrated microgrid controller platform, the IMCP, That also includes, that's an effort that's funded by the Department of Defense, has an Environmental Technologies Program, ESTCP, and that's the funding that's allowing Dr. Karzai and Dr. Lukic to work on that particular platform. And that includes some essentially upgraded cybersecurity features. There are certain standards, of course, for DoD that you have to meet, and the Reops already has a lot of embedded cybersecurity features naturally, but they asked for some additional features as part of it, and so we've included those as well. So, you know, that's certainly one of the issues that a lot of people are concerned about is cybersecurity, particularly for deploying things on the grid and microgrids in particular. And Reops has those features already. Trying to think of any other tidbits I could lay out on you guys while you're thinking of really hard questions for me. No other questions? All right. Well, one of the things I might mention, you know, if anybody listened to Jorge Elizondo's presentation from Hela Technologies, he gives a really good overview of some of the benefits of distributed control systems, which their platform is, which is just what it has. That's the same thing that Reops is as well. It's built for distributed computing. That does make things a little difficult from a programming standpoint, because you have to think about you know, how to make your controls and algorithms more generic. But when you do that, it does allow you to, you know, like what we've done, we've built an energy management application. That energy management application can now work with, you know, 3 devices, whether it's, you know, or 3 other nodes, storage, you know, PV generation, and let's say fuel cell or something else. But now that it's built, it can be deployed just about anywhere. There are a few, you know, programming changes that would need to be made, perhaps specifically for protocols to interface with specific devices on the grid. But the beauty of Reops is its general applicability and deployability for you know, distributed systems. So I would, if you didn't get a chance to watch the Hela Technologies presentation, do that. And while Jorge's talking, think about Reops, because we do, you know, a lot of our platform does a lot of the same things that theirs does. The big difference is that ours is open source and out on GitHub, and Hela Technologies is proprietary. Ours is still in the academic environment, like I said in my presentation, and Hela Technologies has been deployed on multiple locations. So they're ahead of us certainly in that way. But one of the big draws that we have is that we are open source. So I'm going to wait maybe another minute or two. And Frank, I look forward to getting an email from you and starting up a conversation about containerizing. But if no one has any other questions, then we can leave this session and you guys can get a little bit of your time back. All right. Well, here in the United States, it's almost my bedtime. So I appreciate everybody joining this, joining the LF Energy Summit, and certainly learning more about Reops. And you've got my contact information, so let me know if you need anything else in the future. Thanks a lot. We'll end this session.